Okay, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. Let's see, we had some questions left over from last time. So let's see. We had a question here from Oflamio. How does the Bloomberg Terminal work? Okay, I'll see what I can do with that. So Bloomberg terminals are a sort of the leading brand of ways to get financial information. Certainly not the only way. For example, in Wolfram Alpha and Wolfram Language, we have access to lots of financial information. Let me explain what it is and how that all works. So first point is when there are public companies where anybody pretty much can buy shares in the company. So a company like Apple or Microsoft or Google or all kinds of other companies have you can buy shares in the company. So you can buy 0.0001% of the company by spending X amount of money. At every moment, some people are trying to buy shares in the company. Some people are trying to sell shares in the company. So there's a market and people are deciding how much are these shares actually worth. So if suddenly one day it's like suddenly some company looks like it's doing really cool stuff. Everybody wants to buy shares in that company. And so they're prepared to spend so that it will tend to be the case. They say, oh, this company, it used to be that this company shares were $10 each. But people say, well, I'm so keen to buy shares in this company, I'm going to pay $11 for the shares in that company. And other people who own shares in the company already said, great, we'll sell you the shares for $11. Or another thing might be people are like, this company is not doing very well. I want to... I really want to get rid of my shares in the company. Somebody says, well, I'll take them off your hands for $9. And say, fine, I'll sell them for $9. So at any moment, there's always this sort of process happening between buyers and sellers of shares in a company. And how do you determine what the shares should be worth? Well, nobody really knows. It's determined by what people are prepared to pay for them. Now, people will say there are theories in economics about how you determine how much the shares of a company are worth. It's really a question in the end of how much is the whole company worth, because the shares in the company are just defining, like a company might have 1 million shares. And so if each share is worth $100, the whole company would then be worth $100 million. And usually the way it works is that some fraction of the shares in a company, in a public company, are available to the public, and some fraction are held by inside people and so on. Now, I'm trying to remember how many. I think worldwide in the large exchanges there are around 40,000 public companies, maybe in the US 5,000. I'm not sure. I don't remember exactly. Most public companies are quite large. There are some small companies that maybe they were once large and they became smaller, and they're still public companies. They're so-called pink sheet companies that I guess are called pink sheets companies because their descriptions of them were on pink sheets, so to speak. But most companies that are public companies, the whole company is worth billions of dollars. And so when you the shares you have, each share might cost, let's say, $10. You own a tiny, tiny fraction of the company. Okay. So then there's the question of these shares, people are continually saying every day, there's all kinds of people saying, I want to buy shares in the company, I want to sell shares in the company. Some companies are sort of thickly traded in the sense that every day there's a large volume of people saying, I want to buy, I want to sell, and that's happening maybe every second. Other companies, it's like nobody's really paying a lot of attention to this company. So maybe there are only 10 transactions in a whole day of people buying shares, selling shares in the company. And the question of how much the company should be worth, is this really a company that should be worth $10 billion, $100 billion, $1 trillion, whatever. That's really, as a practical matter, determined by how much people will pay for it. There are economic theories. One of the sort of traditional economic theories says it's a theory that says basically the current price of the company should be a measure of sort of the discounted value of future dividends from the company. What does that mean? Well, so a company, when it makes things, like a company might be making, I don't know, cell phones or something, the company is, people are paying money to get those cell phones. So they might be paying, for each cell phone, they might pay $300. But it will cost the company a certain amount to make each of those cell phones, and all the research and development the company does, all the marketing campaigns the company runs, and so on. It might, in the end, be costing the company $280 effectively to make. Those would be the expenses on a $300 cell phone. So the company is then, its revenue, total amount of money it's bringing in is $300 per cell phone, but the amount of money that it is making as profit, as opposed to money that's got to spend in expenses, might be only $20 per cell phone. And so for any company, you can look at its financial data and you'll see a revenue, and then you'll see a net income. And the net income is the profit of what the company, the money that the company sort of keeps after it's paid the expenses that it has. The expenses might be the actual components of the things it's making. It might be the cost of the employees the company has. It might be what it's spending to ship the products here and there, et cetera, et cetera, et cetera. There are other issues when the company is, like, let's say it builds a factory. There are all kinds of questions about exactly how the money that's spent to build the factory is accounted for, because you might build a factory for hundreds of millions of dollars 1 year, but that factory will last you for 20 years. And so the way that accounting is set up, you don't say that all the expense of building the factory is all taken in the year when you actually build the factory. It's spread out over a large number of years, and different kinds of things have the amount of money that's spent on them spread out over different numbers of years in terms of where it shows up as an expense with respect to accounting. So it's a little tricky to figure all of that out. But in the end, a company, if it's going to be a sort of surviving company, in the end, presumably it's got to make a profit. It's got to make more money than it spends. And in the end, when companies make more money than they spend, one kind of expects that the people who own the company will be getting some part of that money. And the way that works is the company pays dividends. It says, if you own a share of the company this year, then the company will pay you $1 as of its profit for that particular, associated with that particular share. Now, there are plenty of, in the technology area, plenty of companies don't pay dividends. In areas like utility companies, power utilities, things like that, they sort of, once you've built the power plant and it's running and so on, it costs a certain amount, but it's going to make money, and it pays dividends to its shareholders. And so one theory of sort of how much a company should be worth is, you wait and you see, you imagine the future, and you say, 20 years from now, this company will be paying these huge dividends because everything, it'll have built up all this stuff and it'll just be making huge profits. You say, well, that's 20 years from now, but what about now? Well, you could always say, well, what if I borrowed the money now and then I would be paying interest on that money? There's an effective value of what the money that would be paid 20 years from now. There's an effective value of that money now based on, I borrow the money and then I'm paying interest for that period of time, the so-called time value of money. And so one theory would be, companies are worth sort of the discounted future value of their dividends. This theory is probably nonsense. This is has been a traditional theory of, that's ultimately what a company is worth. The fact is, what people usually these days, particularly in technology companies, they're usually thinking, the big idea that people have is, I buy stock now for $10 a share. I wait until it goes up to $15 a share, and then I sell it to somebody else who is prepared to buy it at $15 a share, and I make myself a $5 profit. I'm not imagining that sometime in the future the company will be paying dividends. So it's really a matter of sort of trading with other people for these shares, rather than what will the fundamental thing of the company be. Okay, so then the question is, People are trading shares. Somebody's buying the shares for $11, $9, et cetera, et cetera, et cetera. Throughout the day, for any given publicly traded company, there will be prices being set. How are those prices set? Well, every time a transaction is done, that defines a price. So-and-so bought the shares for $11.15. Okay, that's an event. That's a price that was set. Somebody else buys it for $11.10. Okay, that's another price, a little bit lower than the previous one. And so throughout the day, there'll be these sort of little events that are happening of these trades that are going on, and each one has a price that gets recorded. How do those trades work? Well, when you say a company is a public company, if you really get into more of the details, it's public on a certain exchange. So in the US, two big exchanges are the New York Stock Exchange and NASDAQ, the NASDAQ. NASDAQ is an electronic exchange. The New York Stock Exchange is a more sort of human brokered exchange. How do things actually work? Well, in the end, what's happening is people will be saying, I'm prepared to sell this stock for this amount of money. Other people will be saying, I'm prepared to buy this stock for this amount of money. Those have to be matched up somehow. That's, in a sense, what the exchanges are doing, is to make those matches happen. And in the case of NASDAQ, it's happening electronically. In the case of the New York Stock Exchange, there actually is, I think, still a physical place where there are sort of specialists associated with each company who are there with a little booth, effectively, and they're the ones who are dealing with the actual transactions that are happening. But either way, in the end, a transaction happens, and as soon as the transaction happens, the information about that transaction becomes this sort of price fact about that company. And this idea of sort of price facts about companies has been going a long time. It's been going for the whole history of stock exchanges. And back in the day, 100 and something years ago, there was a ticker tape that was quite literally something where there was every transaction that was made, there was sort of it was sort of recorded on a tape, and it was this company, all these companies have IDs, and back in when the stock exchanges were young, 100 and something years ago, there would be companies like T. I think T is still AT&T probably, but there were companies that were they would have single letter acronyms. These days, they're like Apple is AAPL, Microsoft is MSFT. Those are on the NASDAQ exchange. I think that there are usually 3-letter or 2-letter acronyms on New York Stock Exchange, where there are a smaller number of companies and so on. But each one of these is, a company is designated by some ticker symbol, and then that every sort of transaction is MSFT, and then there's some number. I don't remember at all what Microsoft's stock price is now, whatever it is, $500 a share, whatever, I don't know what it is. Every transaction, it's the sort of the ticker name of the company, and then how much the transaction happened for. And needless to say, there's more complexity because there's a spread in the transaction, because somebody is taking a commission on actually doing the transaction, et cetera, et cetera, et cetera. But in a first approximation, there is a price at which that transaction took place. Okay, so now the question is, what happens? So what's being generated is this sort of ticker tape of all these successive transactions, millions and millions of them these days per day. And then the question is, how do you know about that? Well, back in the day, for example, one of Thomas Edison's early inventions was a better sort of ticker tape device for getting the information associated with stock transactions distributed. And back in the day, it used to be distributed by telegraph lines. These days, it's distributed in other ways. And what actually eventually happens? Well, what eventually happens is, from these exchanges are basically putting up electronic information that says this transaction happened, this is the amount the transaction was for, and so on. And so when we from Alpha or Bloomberg making Bloomberg terminals, we're getting the information from the exchanges, sometimes through brokers who provide the information from the exchanges, but it's basically from the exchanges, this series of this was the price that this just happened, this was the price that this just happened, and so on and so on and so on. And that's essentially, when you see prices displayed, that's what's going on. And then, obviously one stores the information on historical prices, and one can go back and see, what was the stock chart through the year or whatever of this particular company, etc. So that's the basic story. Now it gets more elaborate when you're dealing with things other than stocks. There are more complicated issues associated with getting price information for these other kinds of things. And people are often very concerned about just exactly how quickly can you get that stock information. So for example, people have trading strategies. They might have a very simple trading strategy where they say, I'm going to buy this thing as soon as it goes below $100 a share. Okay, and they just set up some order that says buy it when it goes up below $100 a share. But people who do quantitative finance and use a bunch of fancy mathematical methods to try and sort of beat the market, what they're doing is they're doing much more elaborate kinds of things where they may make a huge number of trades. So the sort of extreme case is so-called high-frequency trading, where you might be trading many times a second some particular stock, and you're watching for very detailed things about what's happening as other people trade that stock, or as these prices change. And so it becomes a big sort of issue. Can you get when you're doing that, it really matters what was the price when. And so the price is set at some exchange. Let's say you're trading a stock in the UK and it's on the London Stock Exchange. So there's some moment at which a trade happens on the London Stock Exchange and a price is set for that particular stock. So if you are then sort of comparing that with the price of some stock in New York that's being traded on the New York Stock Exchange, one of the issues is how quickly can you sort of exchange that information? And so people go to very great lengths. I mean, there was a recent effort to put a new fiber optic cable under the Atlantic to be able to get just a little bit quicker information from, for example, the London Stock Exchange in New York and things like this. And if you're doing these strategies where you're like trading many, many times a second, it starts to matter that there's an extra 50 milliseconds, 100 milliseconds of delay in getting the information about that stock trade. But there are all kinds of things that also happen in terms of getting information. Like for instance, there's an exchange. I don't know quite what's happened to it, but there's an exchange that was sort of another exchange that had been set up as a very electronic exchange, where sort of the deal was you simply, if you want to get information about stock trades, it's like a place where it's like a data center where you just pay to have a rack where you can put your computer equipment, and then sort of all of the data, like this sort of a modern electronic version of this kind of ticker tape idea, sort of all the data of stock trades sort of is flowing through this whole data center. And if you happen to have your rack of electronics there, you can pick up the information from it. So anyway, that was a bit of a story about how information about financial transactions gets delivered to people. And one of the questions that's more of a science question, I suppose, is if you look at one of these stock charts, it's always wiggling around seemingly randomly. In fact, it's a pretty good approximation to a lot of stock prices that they are random walks, in the sense that they have an equal chance to go up and to go down. And random walks have all kinds of characteristics and all kinds of things you can calculate about what random walks do. In truth, they're not quite random walks. The most important effect about a stock price is that it can't be negative. That is, or at least in most situations, it can't possibly be negative. A company can never be worth a negative amount of money. You might have said that about something like oil, but there was a time a few months ago when the effective price of oil on the market actually managed to go negative because for various reasons, which, but that's in the normal course of events. Price of stock is always positive. So that's a kind of a constraint on this random walk. And there are also constraints about whether the tail of the random walk is heavy, whether stocks tend to kind of get to larger values more or not. And so there are some deviations from that. But in a first approximation, it's kind of a pretty good approximation to a random walk. And the question is, why is it that way? And is that because of the fact that you're always getting new information about stocks and people are always finding out new things? And so there's always sort of random data coming in, and that's why it's sort of randomly moving around? Or is it more something to do with the dynamics of individual traders who are like, oh, I'm going to buy this, I'm going to sell this, oh, I'm going to watch what the other guy's doing, I'm going to do this, I'm going to do that? And increasingly, in some stocks, if you just look at the sheer volume of trades that are going on, a large fraction end up being associated with things like high frequency trading and other kind of algorithmic, computers working out what to trade, rather than a human saying, "Oh, I really like that company. It's making really cool stuff. I'm going to buy more shares in it." So that it becomes sort of a question of, if you have all these computers with all their algorithms and they're figuring out, I should buy, I should sell, I should buy, etc. What does a collection of computers who are trading with each other, what does that do to stock prices? And maybe that leads to sort of these random fluctuations, and that's actually probably a good thing, because if there's sort of everything's happening randomly and somehow there's a sort of perturbation to this, somehow there's something sort of very surprising that happens, it's still, there's enough randomness going on that the system, another computer will decide this and another one person will decide that, and it's all sort of randomly kept in some kind of equilibrium, kept under control. But if, on the other hand, it's really just the market is just 5 computers and they all have similar algorithms, and something happens in the world and suddenly they all say, "Oh, we've all got to sell," and it's like, okay, great, they're all selling, who's buying? They're the only people in that market. And so when it's like there are only sellers and there are no buyers, what does that do to the price? That means if there are only sellers and no buyers, the price is just going to go down, 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 because eventually you should be able to find a buyer. If you had a $10 thing and you're prepared to sell it for $1, eventually somebody's going to buy it, presumably. But let's say it was, the only things in the market were these computers that were deciding what to do. The price might go to zero. The price might go, it might all go crazy. And so that's a sort of a concern, and it's better for there to be a certain amount of randomness. And in fact, in the markets, one of the roles of exchanges, sometimes controversial, is to stop trading when things go too weird and too unstable. All right. Anyway, a little bit about the financial world. All right. Let me see. All kinds of questions here. It's a question from Parmenides. I had mentioned somebody had asked in a different live stream about a sort of amateur satellite launching, and I was mentioning a friend of mine who had a small microsatellite. I don't know how big they are. They're little CubeSats. I think they're about a few inches across, and they get launched in big collections by satellite launch companies, and then you're up in space. You're 100 miles up, whatever it is. And then the rocket opens up and there's this whole row of little tiny satellites, and it's like they all get pushed out into space, and there they are. They're all floating out in space in orbit. And what happened to this friend of mine is they did not have their act as well together as they should have done in figuring out how they pick up the signals from the antenna, from their CubeSat, et cetera, et cetera, et cetera, and they lost the satellite. So the question is, did they find the satellite again? And the answer is no, they did not find their satellite again. And it's kind of tough because, it's like something goes wrong with your computer and it's in space. What do? Well, you might say, let's reboot that computer. Well, who's going to reboot it? What's been done on deep space probes is that they'll often have, multiple computers, and they'll have mechanisms for sort of failover from one to another. And in the end, they'll have sort of mechanisms to reboot things that are sort of, I actually don't completely know how this works now that I think about it. I mean, it's kind of a weird thing because people are still sending signals to spacecraft that were launched, 30, 40 years ago, when computers were much more primitive. And it's like there's a particular machine code that this computer, that this deep space probe is running. And every so often you can reload new code in there and say, start executing again. The way it actually works, there's a deep space tracking network that's a bunch of radio antennas in different places on the Earth. And as the Earth rotates, different antennas will be sort of lined up to be in the right direction to communicate with a deep space probe that's near Jupiter, let's say, or that's out, past Neptune or whatever else. And the way it works is they're all sort of time sliced. And so at a particular time of day, the such and such spacecraft knows to kind of wake up, and that's when data will be sent to it. And I guess also the other way around. Maybe it's more important the other way around. There'll be a particular time of day when that spacecraft, when the satellite, the radio telescope dishes will be turned in the direction of that particular satellite to say, okay, what do you have to say today? And then it's possible to upload new instructions to these spacecraft and get them to start executing those new instructions. And you better not make too many coding mistakes, because if things go horribly wrong, you could end up with well, I actually just shut your antenna down, never have it powered up again. And then it's like, well, I'm sorry, the thing, your spacecraft is somewhere near Neptune and it's never going to listen to you again. Game is over. So that's a thing to avoid. It's impressive that they're like, what is it? I guess the Pioneer spacecraft are now gone. Is that right? And the Voyager spacecraft, which are still in communication at like 35 years after their launch or some such. And by the way, I mean, the other issue is you've got to maintain power on a spacecraft. And how do you do that? Normally in Earth orbit, satellites are powered by solar panels, because we're close enough to the sun that we can get enough solar radiation that we can use photovoltaics and actually produce power. And when you're making a deep space probe, you can't do that, and instead they use essentially nuclear batteries, where they're using where you're too far from the sun, so you can't expect to get enough solar radiation. I mean, it's just like on the Earth, it's easier to have solar panels work near the equator than it is near the poles, because they're just the angles are such that you just get more sunlight near the equator than you do near the poles, which is why it's colder near the poles. But when you're out sort of past the orbit of Jupiter, the sun is a little tiny spot in the sky, and so it doesn't. You're not able to get enough solar radiation. So instead, you have to use these kind of nuclear. These not like a nuclear power station where you're, but more just you're using nuclear decays to produce heat that allows you to make electricity. Okay, let me see. Well, gosh, many questions here. Okay, so there's a question here. What are Feynman diagrams? Okay, this is going to take us in a completely different direction of talking about things. So Feynman diagrams are a thing in physics. They were actually invented by a late friend of mine named Dick Feynman. He invented them in the 1940s. What are they? Well, when you have, if you look at matter on a very small scale, you find things like electrons. Electrons exist in atoms and so on. The nucleus of atoms is made of protons and neutrons, which in turn are made of quarks and gluons. Sort of around the nucleus, the stuff responsible for all the sort of chemical effects of atoms are the electrons that exist sort of in the outer part of the atom. So one question is, if you take a photon, particle of light, and you shine it, you have a beam of photons and you have a beam of electrons, and the two things kind of hit each other. Sometimes an electron and a photon will kind of hit each other and scatter away. So and that process is called Compton scattering. After the chap who discovered this, a photon can interact with an electron. Okay, so the question is to describe that process, to say just how often, if you have a photon coming in this direction, it has a certain energy, and an electron coming in this direction has a certain energy. What's the chance that those two things will actually scatter from each other? And in effect, it's often described in terms of the cross section. What does that mean? Well, imagine you're firing an arrow at a target. The question of what's the chance that you hit the target? Well, it depends a bit on how big the target is. As you put your arrow in different places, the bigger the target, the more likely you are to hit. The more likely the cross section is. When the cross section is larger, the probability of an interaction between the arrow and the target is bigger. Actually, in the kind of strange sense of humor of nuclear physicists back in the day, the usual unit of cross sections for nuclei, for what's the chance that an electron will hit a nucleus, for example, it's measured in barns. Like, you could hit. You should be able to hit this barn, like a barn on a farm type thing, from miles away. Well, it's actually a nucleus, which is really, really tiny, so it's not such an easy thing to hit. But it's kind of as a kind of a joke. These things called barns, and typical nuclear, the sort of effective nuclear cross section for interactions is what are barns. When you're dealing with particles, for example, the probability that two protons, if you fire two protons at each other, the probability that the effective cross section of the protons is, well, it used to be on the order of 40 millibarns. Actually, as the energy, typical particle accelerators, as the energies of particle accelerators have gone up progressively, as the energies of protons go up, it turns out that the chance that they interact increases slightly. So I think it's probably maybe 150 millibarns at the highest energies that particle accelerators that crash beams of protons, well, more often beams of protons and antiprotons together, will reach. Okay, so the question is, how do you figure out, given that you have an electron with such and such an energy, a photon with such and such an energy, maybe just an electron, that's another, I think it's called Moller scattering, is scattering of electrons by electrons. Let's actually talk about the electron-electron case, probably a little bit easier. So you've got two electrons, they're being fired at each other, and you've got these two beams of electrons. What's the chance that they scatter? Okay, how do you work that out? Well, let's see. This is what Feynman diagrams do. And they're basically a mathematical procedure for working out the chance that those two things can interact. So how do electrons interact with each other? Well, the fundamental form of interaction between electrons and photons is an electron can emit or absorb a photon. So essentially, if you draw that as a diagram, it's like there's a line that represents the electron, and then coming out of it, there might be, it's usually drawn as a wiggly line that represents the photon. So either, the electron is going along, it either emits a photon or it absorbs a photon. And that's represented by this piece of a diagram in which there's a line for the electron and there's a line for the photon. Okay, so how does electron-electron scattering work? Well, there's a line for one of the electrons, there's a line for the other electron, and then what's happening is it's exchanging, there's an exchange of a photon between these two electrons. So you draw another little line, the wiggly line that joins the line for one electron and the line for the other electron, and that represents the exchange of one photon. Actually, officially, it's a so-called virtual photon. It's a photon that isn't the kind of photon that just goes on forever and eventually you can see it in your eye or something like this. It's a photon that is just produced for a very short period of time by one of these electrons, then absorbed by the other electron. And the deal is, in quantum mechanics, if you produce things for a short amount of time, they kind of don't have to have their usual characteristics. Like photons are usually massless particles traveling that travel at the speed of light. In a virtual photon doesn't have to be massless. So long as it sort of survives for a short enough time, the amount that it can have an effective mass that is something that, depending on how short the time is, as the time gets shorter and shorter, it can be sort of more and more wrong about the mass that it has. So anyway, how do you represent electron-electron scattering? So the first order Feynman diagram is just, you've got these two lines for these two electrons, you've got one photon being exchanged between them. Okay, so what Dick Feynman then did was he gave these rules that say, given that that's the diagram that represents the scattering event, scattering process, what's the chance that that scattering process happens? So in that particular case, the answer is well, I can tell you what it is. It's okay. So the first thing is, what's the fundamental probability that an electron emits a photon? Okay, it's governed by a thing called the fine structure constant, usually denoted alpha, and well, the actual probability, the probability for a single emission is actually a lowercase e, which is sort of the square root of the fine structure constant. But let's ignore that. There's always two ends to the line, so it's always an e squared. And then the fine structure constant alpha is equal to about 1 over 137. So it tells you that kind of the basic parameter that determines sort of how likely the electrons are to emit a photon is this alpha 1 over 137. Okay, so then if you want to work out the actual probability, there are some other terms. So I mean, just to tell you, it's been a while since I thought about this, but that particular thing is there's a thing called the Dirac gamma matrix, which is so there's a formula basically, involves p slashes and gamma mu's and 1 over q squareds and so on. The most important part of that particular formula is the alpha, the fundamental probability of an electromagnetic process happening, the fundamental probability that a photon will, an electron will emit a photon, and then there's a term that is proportional to 1 over the square of the momentum transfer. So if one electron is kind of kicking the other electron by sending out a photon, the photon is transferring some momentum, and that momentum is kind of, the one electron is going along, and it's going to kick the other electron. So for example, the electrons might be initially going straight at each other, and then they kick each other to the point where they scatter and they go at a different angle. The size of that kick is proportional to the amount of momentum transfer, and the formula in the Feynman diagram, the Feynman rules, is there's a 1 over q squared, where q is essentially the momentum transfer. And so anyway, you put all these things together, you eventually get a formula for the probability of the scattering event that is electron-electron scattering as a function of the momentum and energy of the electrons and so on. Okay, so what happens is the first approximation to that is you exchange one photon. But you can also, the tricky thing with Feynman diagrams is there's also higher order Feynman diagrams. It's like, that's the first order approximation. The next approximation is you exchange 2 photons. Well, if you imagine these diagrams, it's that when you're exchanging 1 photon, it's just there's 2 lines and there's 1 wiggly line between them. Okay, great. When there are 2 photons, it gets a little bit more complicated. The 2 photons can either be parallel, they can cross over. There are a bunch of different diagrams that for where the photons can go. Each one of those diagrams, the Feynman rules tell you what essentially the probability implied by that diagram is. And you're going to add up all those. Actually, they're not probabilities, they're so-called probability amplitudes, which can be negative and so on. And when you add them all up together and take the sum of them and square them, you get the probability. But in any case, you get all these different pieces, and each one has certain rules, the mathematical rules that tell you how to compute the thing. Okay, so you say, well, I did the first order one, that was alpha times something or other. And now, but why don't I have to, how many orders do I have to go to? Well, the second order one involves alpha squared. The third order one involves alpha cubed. The second order one involves alpha squared because there are 2 photons involved, and each vertex, each end where a photon connects with the electron, it gives you 1 square root of an alpha. So the 2 ends of each one of those photons gives you an alpha. Okay, so the good news is if alpha is 1 over 137, then by the time you're at the second order, it's 1 over 137 squared. Third order, 1 over 137 cubed. So that gives you the sense that you don't have to go to very many orders. You're going to be able to get the right answer by just going to a small number of orders in this what's called perturbation expansion to work out the scattering probability. And so what happens with Feynman diagrams is one is doing these calculations. And the calculations get more and more elaborate. As you go to higher and higher orders, the calculations get more elaborate. So first order is pretty easy. You can kind of do those by hand. Second order, it's getting a little hard. There's at least 1 loop happening, and there's integrals you have to do around that loop, and they're integrals over 4-dimensional space, and it's a little bit tricky. And by the time you're at third or fourth order, the things are getting really hard. And that's actually why when I started using computers to do sort of mathematical calculations, one of the big things I wanted to do was higher order Feynman diagram calculations where you're working out many loops. And in fact, the one of those that's been worked out in most detail is a thing called the anomalous magnetic moment of the electron. And that's been worked out to 8th order. And at 8th order, you're routinely spending years of computer time doing all the calculations for these Feynman diagrams. And by the way, by the time you've worked things out to 8th order, you are dealing with, 10 decimal places or more of precision. So it's one of the most remarkable successes of sort of physics has been the correct calculation of things like the enormous magnetic moment of the electron, which have been, with a lot of effort, they're calculated using these Feynman rules. And by golly, you get the right answer. You measure it in an experiment, and it's exactly right. It gets a little tricky because by the time you're at that level of precision, you're starting to see effects from things that aren't just interaction between electrons and photons, but other kinds of virtual pions and all kinds of other things. But anyway, that's the idea of Feynman diagrams. So they've been very successful in studying interactions between electrons and photons. It wasn't obvious how they do studying other kinds of interaction processes, let's say between the pions that hold the nucleus together and protons. Those are much stronger interactions. So this idea that you can just work out the first order and the higher order terms will be small doesn't work anymore, because the equivalent of alpha is a thing that's of order 1, or even worse, 10. And if it's of order 10, then the first order term has a coefficient of 10. The next order term is 10 squared, 100. So it's bigger. So you're not getting to things that are smaller. But in 1973, there was this phenomenon discovered called asymptotic freedom, which tells one that when you're dealing with quarks and gluons, which are the things that are inside things like protons, then the higher the momentum transfer, essentially the more energetic things are, the lower the effective coupling constant, as it's called, the equivalent of this alpha quantity gets. And so there's as you increase the sort of energies, the effective coupling goes down, and it's quite quickly, it's 0.1, and then gets even smaller than that. And that means that you can use sort of Feynman diagrams and this so-called perturbation expansion of first order Feynman diagram, next order, next order, next order, and expect to get the right answer. Now, I mean, there are a few footnotes here for the little bit more mathematically inclined folk. One of the footnotes is that in the kth order, there are at least k factorial different diagrams, possibly more. And that means that, so you've got a formula that says alpha to the k times k factorial. Well, for any value, so k factorial, like 10 factorial is 10 times 9 times 8 times 7, 1. 10 factorial is going to be, that's a bit smaller than 10 to the 10, but it's something where for any alpha to the k times k factorial, eventually the k factorial will always be bigger than the alpha to the k. And so that means that eventually at some very high order, 100th order, with incredibly complicated diagrams, there'll be so many diagrams that you'll expect that just the number of diagrams will make the contribution of the 100th order be really important. And that's bad news, because what we're doing is we're saying, let's just work out this answer by just looking at the very low orders of Feynman diagrams. Nobody really knows why or whether high order Feynman diagrams, they don't appear to be important, because otherwise we wouldn't be able to get such good answers for things like the enormous magnetic moments of the electron. But quite why isn't completely clear. Some people argue it's really a square root of k factorial. Some people argue that there's more cancellation in these diagrams than you would expect, and so it's not really k factorial at all, et cetera, et cetera, et cetera. But nobody really knows. And so that's one of the sort of continuing mysteries of quantum field theory and Feynman diagrams and so on. Now, another thing is, if you want to work out the scattering of electrons in quantum electrodynamics, the theory of electrons and photons, is it really necessary to do all this Feynman diagram calculation, or is there a better way? Well, for about 70 years now, people have been looking for a better way. Dick Feynman himself always used to say, I can't believe there isn't a better way to do this, particularly as he saw people going to these incredible lengths to do, year-long computer calculations to work out some of his kinds of diagrams. Well, so far, we don't know a better way. There are some hints from ideas that come out of things like string theory and more conformal field theory. There's a fancy area, which I could explain sometime, of quantum field theory that maybe, possibly, conceivably suggest that there's a way to sort of relate what happens with Feynman diagrams to what happens with things that look much more like the theory of gravity, and that there might be a way to sort of be able to just sort of work out, this is the answer. You don't have to go and work out all the individual Feynman diagrams. Actually, with our current approach to a fundamental theory of physics, it's looking quite likely that there will be a way different from that way to do computations in quantum field theory and do computations of like the interactions between electrons and photons. that will be quite direct and will involve looking at sort of the discrete elements that lie underneath electrons and photons. The bad news is we know how to do it for sort of bulk quantum fields, but we don't really yet quite understand what an individual electron or an individual photon is like. And so we can't quite yet do those calculations, but it's something that is looking quite promising and maybe a way to kind of finally do what Dick Feynman thought was possible, which is just don't work out all those details with Feynman diagrams. But anyway, so that's the idea of Feynman diagrams. They're basically a representation of microscopic processes that involve things like electrons and photons, and they give you a calculational way to figure out what the probabilities of those kinds of interactions are. Let's see. So question here. Okay, it's a question here from Pranjul. How do holograms work, and why don't we have more holographic technology? Okay, so just a second. Okay, how do holograms work? Well, first of all, what is a hologram? So when we look at a picture, we're basically looking at a pattern. Well, let's say we look at a computer screen. The computer screen is lit up. There's basically light coming from each part of the computer screen to our eye, and we're seeing each pixel on the computer screen might be a different color. So there might be a red pixel next to a blue pixel, next to a white pixel. We see that as some piece of something or other. But what's happening is there's light coming straight from the individual pixels on the screen. Each of those pixels is emitting light. And when it emits light, it might be slightly directed, but it's more or less emitting it in all directions. And some of that light, when we're looking at the screen from a particular angle, some of the light from that pixel will hit our eye and we'll say, oh, that's a red pixel. Okay, so that's how ordinary vision, ordinary images work. Okay, but what's happening at a, let's see how to explain this. Okay, so in that picture, what's going on is it's as if we have little sort of particles of light that come from the screen and hit our eye, and it's like a red photon comes from the screen, hits our eye. We say, okay, that was a red pixel. Okay, but there's a different view of how light works, which is not in terms of photons, particles of light, but instead in terms of waves. So we can also think of it as being, and these are sort of complementary points of view about what light really is. We can think of light instead as a wave, where instead of there being a photon that is like this particle of light coming from the pixel, instead the pixel is generating this wave that's coming out of the pixel that's continually it's a continual sort of variation of the electromagnetic fields that correspond to sort of what the light is made of. It's that continuous variation, and that's a sort of a wave that again is reaching our eye and so on. Now, when we think about light, both of these descriptions are sort of mathematically valid. When we think about sort of the mathematics of representing light, which is ultimately an electromagnetic wave, when we think about representing it, both of those descriptions, the photon, the particle of light, and the wave, they both end up, when we actually calculate what will be the intensity of electromagnetic radiation that falls on our eye, they're really just really different ways to calculate the same thing. Sometimes if we have, for example, when we have X-rays, gamma rays, those are electromagnetic radiation that has much shorter wavelength, much higher energy per photon, it's much more like, oh, there's an individual photon, there's an individual photon. And when we have radio waves, it's much more like, oh, it's just a smooth wave that's going on. But they're both kind of limiting versions of the same mathematics. Okay, so when we start thinking about light in terms of waves, one of the things that we might try to do is to say, let's try and reproduce the wave fronts. Let's try and reproduce the waves that exist in the electromagnetic radiation. Forget about the pixel on the screen emitting a stream of photons or something. Just let's set things up somehow so that we reproduce the sort of the wave fronts of light in the right way. And so what holograms are doing is essentially setting themselves up to reproduce those wavefronts. It's like, forget what the actual pixels are like. All we care about is reproducing those wavefronts. And one of the things that's tricky is that in order to reproduce those wavefronts, when you have if you have just a stream of photons, boom, 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 photons coming out, it doesn't really matter just exactly at what time each photon came out. It's just like, okay, I received a red photon. Great, I'll receive another red photon, etc. When you're dealing with waves, it really matters. Imagine waves on a string. You're wiggling the string at one end, and it's having this wave go back and forth. It really matters if you suddenly change how you're wiggling it. It really matters what the timing of that changed wiggle is. It matters when that wiggle is relative to the sort of the undulations in the wave, the phase of that wiggle. The phase meaning the sort of phase of a wave is when the wave goes from being sort of zero up to its maximum value, goes back to zero again, goes negative, goes back to zero. The phase is sort of where you are in that cycle of going from zero back to zero again. And so it can really matter if you're sort of changing a wave. It can really matter where that change is relative to the phase of the wave. And so what has to happen to make a hologram, to reconstruct this set of wavefronts and so on, you've got to basically be able to get, you've got to be able to have the right phase information. You've got to be able to have all those pieces of waves be constructed with the right phase. So if you could do that, then you can make this sort of, you can fake up the exact wavefronts, the exact pattern of waves that corresponds to the light. If you can do that, then as far as your eyes are concerned, you're just seeing the light as it would be constructed with those wavefronts. So the question is, how do you fake up that phase? Well, when you use lasers are an important piece of this. So when you have an ordinary light bulb, for example, or for example, the fluorescent lights that usually are used for the backlighting for computer screens, those kinds of things. Actually, they're probably now LED lighting, but either way, any of those forms of lighting have the feature that they are not coherent in the following sense. You can think of them as producing pieces of light, let's say photons, or they could be waves. You could think of them as waves, but whatever they're doing, they're just like, okay, there's you're producing one little lump of light, one little photon, one little piece of wave, and then a little bit later you produce another one, and they're kind of randomly timed. There's no coherence between when those pieces of light are being produced, and that's because, let's say you're producing light by just having an incandescent filament. You just heated up a material. What's happening is the atoms in the material are being put in excited states, and as they decay down to their ground state, they emit photons. But when that decay happens, it's completely random. So that means that the photons that are coming out from the incandescent light bulb are coming out at all different times. There's no coherence to when they come out. Okay, lasers work differently. In lasers, what happens is the word laser stands for light amplification by stimulated emission of radiation. What's happening is that you are setting things up so that essentially all the photons in sort of one piece of the laser are all coming out together, and roughly again, it gets us off into a slightly different topic, but photons are a type of particle called a boson, and bosons are particles that kind of like to all be in the same state. If you start adding photons to something, the chance that you can add a photon to something is larger if there are already photons in the state of the photon that you're trying to add. And so that means that in a laser, what you're doing is you're basically you're organizing it so that there's stimulated emission of radiation, and as opposed to the spontaneous emission of radiation that happens in like an incandescent light bulb, you're stimulating it by having other photons be there, and those other photons are saying, we're in this state, hey, come join us. And the way photons work, or boson particles in general work, is they want to do that. And so they all end up in the same state. They all end up with the exact same frequency, the exact same color of light, and they all end up with sort of a wave that is coherently produced. And so in a laser, you get coherent light, and that means that it's not just photons coming out at random times, everybody's in phase. And that's what you need in order to construct, well, okay, in the simplest form of hologram, that's what you use in order to construct, in order to set up the phase relationships so that you can get the sort of reconstructed wavefront, so that you can see things in a way that is sort of, you've constructed this pattern of wavefronts in space, and as you move your head around, for example, you are seeing the right pattern of wavefront that corresponds to what the object would look like if the light was coming from that angle or that angle. And I should have said, when a pixel is emitting light, I think I mentioned, it's sort of emitting the same light in all directions. When you've constructed all these wavefronts, the wavefronts can be different on this direction and that direction. And that means that it's just like if there was a physical object there where you look from a different angle, you look from another angle, you see different things. You've constructed the sort of the structure of the wavefronts of light that will correspond to that, and you can then look from different angles. Now there are also things called white light holograms that well, there's a whole collection of different stories here. But okay, why is it difficult to make holograms? So what happens is when you make a hologram, what you're doing is you're in the simplest way, you're shining a laser at this pattern that is exactly producing the right wavefronts. But that hologram, in order to make those exact right wavefronts, the hologram has to have little markings on it that are about the wavelength of light in size. Okay, so light wavelength might be 500 nanometers, 0.5 microns. That will be some fraction of a millionth of a meter. So in order to, what you have to do to make a hologram, you have to be able to have essentially a display. Okay, to define how those wavefronts are going to work, you have to be basically sort of telling the pieces of light whether they're going to be sort of emitted or not. But you have to do that at a size that is comparable to the wavelength of light, and the wavelength of light might be a fraction of a millionth of a meter. And that means that in order to do that, in order to make a hologram, you have to be able to have something where you can have sort of features that are of that order of size. Now, if you're sort of etching it out of some plate or something like this, it's pretty easy to make something that's that small. If you wanted to make it purely electronically, if you wanted to make it like a display, like the light emitting diode displays that we have, or the liquid crystal displays that we have, if you want to be able to make sort of pixels that are small enough to be able to sort of control light down at scale sizes about the wavelength of light, that's not been possible yet. Perhaps that will eventually be possible, and that will allow one to actually have a display that is sort of a fully holographic display, where every individual pixel on the screen is not just saying emit light in all directions, but it's a piece, it's controlling just a part of the wavefront of the light that's being produced, so that you're able to construct that sort of elaborate wavefront that lets you kind of look around the display and look from different angles. There are a whole bunch of different ways to sort of approximate this using like lenticular displays where you have stripes that are going in different directions and so on. But I think the thing that hasn't yet been possible is to make displays where you can be playing a movie right at the at sort of the wavelength of light scale size, so that you can construct this kind of constructed wavefronts of light. Now, in reality, us humans don't really need all the precise wavefronts of light constructed, because we just have two eyes. And really, most of our perception of depth comes from the fact that we have a parallax. We're looking at an object from two slightly different angles. And as we compare what the object looks like from those two slightly different angles, we're getting a sense of how far away the object is. And so if what we're trying to do is just give us a sense of depth, we don't need a hologram. We need a hologram if we want to look to the side of the object and so on. But we don't, and we don't need that. We just need to be feeding the right signal with the right parallax to our two eyes. And for example, in VR headsets, virtual reality headsets, this is kind of what's done, is you're just sort of feeding the you're feeding sort of the image from a slightly different angle to each, as taken by a camera at a slightly different angle to each eye, and then you're getting the perception of sort of three-dimensional stuff with depth. And the way that a VR headset works, it's measuring with an accelerometer, it's measuring your head moving around, and it's using that to be able to say, oh, well, you moved your head to that angle, so I'll show you what that object looks like from that side. And one of the big issues with VR is making sure that that happens quickly enough, because our brains are really sensitive to when we move our head, does what we see change? And if we move our head and what we see doesn't change, it has a little delay, that makes our brains very confused. And for somebody like me, for example, with earlier VR headsets, it would take me only about a minute to start feeling incredibly motion sick from the kind of lag that existed between the move your head part and what the actual image looks like. But okay, so that was a little bit of an attempt to talk about holograms and why they're not more widely used. So I think we should be wrapping up fairly soon, but let's see what we can talk about here. David Brown asks, have I read a book called The Deep Learning Revolution by a person called Terry Sejnowski? Terry has been a good friend of mine for many years, and he sent me many versions of that book. In fact, I even suggested its title. It had a much more nerdy title before that one. But have I read every page? I must admit, I probably haven't read every page, but it's a book about the history of neural networks, which Terry was himself much involved in. And it's about it's a very upbeat book about the history of machine learning and neural networks. And Terry himself has been particularly involved in the question of modeling actual human brains and seeing to what extent we can make computational models that approximate human brains. And then the realization that, gosh, those computational models are actually good for building technological kinds of things, and for being able to sort of do things like object recognition using artificial neural nets. IO something or other is asking, how closely do I follow the field of AI? I think it would be fair to say that I like to think that I don't follow the field. I like to think that I lead some of the pieces of that field, that I'm more leading than following, so to speak. But yes, I've been involved in a lot of things that have been at different times called AI over the course of many, many years. What one means by artificial intelligence, sort of intelligence implemented by computers, has changed a bit over the years. And in a first approximation, as soon as we really get good at doing something, it's no longer considered artificial intelligence. It's just software of some kind. We could talk about some of the things that have happened in that regard. But the whole field of kind of what it takes to achieve sort of human-like performance in different areas is there's lots of different pieces to that. For example, our Wolfram Alpha system that powers computational knowledge and things like Siri and Alexa and so on, that's an example of something which for a long time was thought of as being sort of a sort of an ultimate goal of AI, of artificial intelligence, was to make a question answering system that could answer questions asked in natural language about things in the world. And for a long time, people found it very difficult to do that. We finally sort of cracked that problem when Wolfram Alpha came out back in 2009. But in a sense, the way we cracked it wasn't a very brain-like thing, because what we're doing is, when you ask, I don't know, Wolfram Alpha, you say, what's the population of New York divided by, I don't know, Luxembourg or something. What it's doing is it's taking that natural language and it's converting it into this precise computational language that says the entity, New York City, it is a city, it's this and that and the other, divided, this function, divide, the population property of that, the function divide, et cetera, et cetera, et cetera. It's turning it into something which is a computational language, a language built to be understandable, both to represent things that we humans care about and to be directly understandable to a computer. And so, in a sense, what we've achieved there is a very AI-ish thing. We've achieved this, you can answer a general knowledge question. But the way we've done it is something much more sort of technological. And some of what, for example, Terry writes about with respect to deep learning and so on, that's a story of, can you do things where where in a sense we aren't describing the algorithms by which it works. We're kind of expecting it's sort of a magic thing that can just learn from examples. And so a big piece of the kind of this whole sort of story of neural nets and deep learning is if you give a bunch of examples of pictures of cats and a bunch of examples of pictures of dogs, and then you show a picture, do you correctly recognize when it's a picture of a cat and when it's a picture of a dog? And it wasn't clear that was going to work. For many, many years, people had done sort of built simple versions of that, and it didn't work. I mean, this got started in the 1940s. People had the idea of doing this. By the 1950s, there were already sort of test examples made with electronics that tried to do this, and it fundamentally didn't work, or it worked only in very restricted cases. You know, for example, by the 1980s, doing optical character recognition, recognizes that an A or a B or a C, whatever, that got to be pretty good, so long as you knew there were 26 targets, so to speak, and you could kind of fix up the errors by knowing this is a plausible word with these letters going together and this isn't. That ended up being something that could be done. But when it came to, oh, here are there are about 5,000 picturable nouns in English, nouns that represent sort of generic things that you could make pictures of, like, you know, a chair, a table, a cat, a dog. There are about 5,000 of those in English. And if you say, can you recognize, given a picture, which of those 5,000 things this thing is a picture of, that hadn't been possible. And what people imagined was that nobody really had any idea how many examples you needed to give and how the neural net needed to kind of learn to process that. And then in 2011, actually, due to sort of a chance thing that happened, there was these types of so-called deep learning neural nets that had many layers of kind of functions that were being performed on the data. You could kind of try and train one of those things. It's a very arduous process of, oh, you see, what does it do with this input? Oh, no, that's not right. You know, propagate back the error that happened with that input. Okay, show it another input. Oh, that wasn't right. Propagate it, you know, the error was in this direction. Propagate that back. And you slowly try and tweak how the thing works. And what wasn't obvious was that that tweaking would ever actually work and how many samples you'd need. So the answer ended up being, for 5,000 objects, you need about 30 million samples. And the training takes, well, when we first did it, which was 2014 or so, it took about 3 months of CPU time to do the training that was needed with 30 million samples. Now, by the way, these days that's much faster because we've already pre-trained a lot of things. So we don't need to start from scratch, kind of learning how to see a line, learning how, I mean, what's happening inside is not as direct as learn how to see a line, learn how to see a circle. It's all smooshed together, but that's effectively what's happening. But at this point, we already know the basic sort of features to pick out of a picture, so we can sort of transfer that learning from one neural net to another. It's kind of like it's like we can do a little bit of brain transplanting, which we don't get to do in humans, and it wouldn't work on humans probably for all kinds of reasons. But we can kind of take these neural nets and we can kind of say, there are these layers, you can use those, and now you kind of learn from the output of those. And so the thing that was surprising, 2011, was discovered that yes, you know, if you put enough effort into training and you have enough examples, you can actually recognize those 5,000 picturable nouns decently well. And that kind of started this whole sort of revolution of deep learning, which is kind of a decent fraction of the way through its trajectory. And I think what's happened is first there was image object recognition, then different kinds of things like speech to text was another one that got solved a few years ago. Text translation is another one that's sort of in decent shape now. For example, handwriting recognition still isn't quite there yet. If you can see the person writing, so you can see the sort of motion of the stylus, it helps you a lot. But if you're just taking a picture of the handwriting, not quite there yet. That'll probably be there in another couple of years. Then other kinds of different things that get to be possible. But yes, there's a big story there, and I'm happy to talk about it another time. Let's see, maybe one last question, and then I should wrap up. Oh boy, okay. There's a bunch of philosophical questions here. Maybe another time I'll. Oh, there's so many interesting questions. You guys are You guys are this is unfair. I'm supposed to go do my day job here. There's a question here from Mitchell. Is it possible that long in the future, the universe will mostly consist of iron stars? How would iron stars affect planets with iron cores orbiting these stars? Well, okay, what's going to happen in the universe in a long period of time? One of the things that seems to be happening is everything's turning into a black hole. So, at the center of our galaxy, there's this giant black hole. It's like a giant garbage disposal at the center of our galaxy. And steadily, slowly, things are falling into it. And when we have a star, for example, that's a bit more massive than the sun, stars have different life cycles. Some of them turn into supernovas. One's bigger than the sun, turn into supernovas. The sun will turn into a white dwarf. Some stars just catastrophically collapse into black holes. But the sort of the end state. Okay, so there are white dwarfs. There are neutron stars. There are black holes. Those are three common end states for stars. I guess if you wait long enough with a white dwarf, I would suspect that it does indeed turn into something that's just full of iron. Why on earth should things turn into iron? The reason is a slightly tricky thing. So if you look at the different chemical elements, there are like 100 and something known. Each chemical element, hydrogen, helium, lithium, beryllium, boron, etc., each successive chemical element has a larger number of protons in its nucleus. So you go from hydrogen with 1 proton in its nucleus to uranium with 92 protons in its nucleus, and then off to the various kind of radioactive elements. I think we've got up to about 122 maybe now is the highest element that's been made, although it doesn't survive very long until its nucleus falls apart. But anyway, so you have all these different kinds of nuclei, and these nuclei are all bound together by the strong nuclear force. And the one that's bound sort of the strongest is the one sort of in the middle of the periodic table. It's iron, and actually iron 56, isotope 56 means 56 protons plus neutrons in the nucleus. That is the most tightly bound atomic nucleus. And so if you're kind of saying, well, if you throw all these neutrons and protons together and so on, you get to the point where they have sort of the maximum amount of energy that you sort of go to the minimum energy state. It'll be the thing where they're all bound together like in iron 56. So that's why iron 56 is sort of an end point to a bunch of these nuclear reactions. Now, when you have a big star and you've sort of smooshed together all these nuclei, actually it'll turn into one big nucleus. That's what a neutron star is, just a 10-kilometer across sort of giant single atomic nucleus. But a black hole is what happens when the amount of gravity is larger, and it gets to the point where the escape velocity is the gravity is large enough that the escape velocity is more than the speed of light, and you end up with something which has an event horizon where light can go in one direction but not the other. So it looks to everybody outside as if it's black with no light coming out of it. So the likely thing is that a lot of our universe is going to turn into black holes. It depends in detail on the expansion rate of the universe, whether things sort of exactly what happens there. But I think the main story is things turn into black holes. Now, if you ask the question, if you're on a planet orbiting a star and the star turns into a black hole, what does that mean for you on the planet? Well, the process of turning into a black hole is a pretty violent one. And so that's not a good thing for you. Then will be, I actually don't know. It's a good question. The shock wave generated by gravitational wave emission from for example, a black hole merger. I don't know what that would do to a nearby planet. So, for example, there have now been about 50 black hole mergers observed. So these are black holes which are orbiting each other, and then they slowly spiral, and eventually the two black holes hit each other, and then they merge together. And that's a very violent event. It's been observed in the last about 5 years by gravitational wave detectors. About 50 of those mergers have been seen. And it's fairly amazing because those mergers are violent enough. They release enough gravitational radiation that we can detect it even halfway across the universe. And for example, at this point, I think the largest, furthest away one that's been seen is 7 billion light years away. So that's half the age of the universe. That's halfway across the universe. It's remarkable that we can see an event that took a few seconds to happen 7 billion years ago, halfway across the universe. And that's what happens when you see the merger of two black holes. But when that black hole merger happens, I think the very first black hole merger that was seen is much closer than that one. The amount of energy released in gravitational radiation was 1.5 times the mass of the sun. So in about a second or two, there was gravitational radiation. Gravitational radiation is sort of ripples in space-time, in the curvature of space-time, that produce forces of deformation on objects. So in the universe is expanding. What does that mean? That means that the very structure of space is expanding, and there's sort of a small force that's trying to pull things in space apart. It's a weak enough force that when it comes to a star, a galaxy, something like that, those things are bound together much more strongly than the force that's pulling things apart by the expansion of the universe. But there's a small force that's pulling things apart by the expansion of the universe. When you have a gravitational wave, it's a sort of it's a kind of a wave, like a water wave or anything else, but it's a wave of deformation in the structure of space-time. So it's a wave where things are being sort of, space-time is being pulled apart, being compressed together, being pulled apart, compressed together, and so on. These waves travel at the speed of light, and they're small deformation waves. And so any material object will be deformed by those, will have a small force of deformation associated with those gravitational waves. And so, for example, the gravitational wave detector basically works by having these masses that are a certain distance apart, and as the space-time deforms, it pulls these masses further apart, or they go closer together. The space-time is being deformed, and the gravitational wave detector is measuring that. So the question that you might ask is, if you were on a planet near a black hole merger, what would happen to you? There would be this intense burst of gravitational radiation that would be where it's like the equivalent of the whole mass of the sun being turned into gravitational radiation in a second. So that's very intense gravitational radiation, intense enough that, a third of the way across the universe we can detect it. So what would happen to you on a planet nearby? Interesting question. So I think the real question is, what is the would everything on the planet be sort of torn apart by the gravitational wave going through it? I would suspect the answer is yes, but I don't actually know. Let me think. Let's see. Gravitational plane wave. Well, it isn't a plane wave. Sorry, I'm going into physics speak. It's probably better approximated as a spherical wave, something where the fronts of the wave, instead of being all parallel, are all sort of spherical shells. And so what would that do? I think what would happen is there will be violent tidal forces. Tidal forces meaning, like on the Earth, that the water on the Earth for the tides is both pulled by the moon when it's closer to the moon, and it goes further away from the Earth when it's further from the moon. That's because of the difference in the forces associated with pulling the center of the Earth and pulling the stuff that's slightly closer to the moon, slightly further from the moon. So it tends to elongate things in a certain direction. So my guess is that there will be sort of violent tidal forces on the planet, and I think it would be tough to survive a solar mass of gravitational radiation sort of passing through your planet. But I'm not sure. But let's assume you survived that. And that would be a black hole merger. And I think the formation of a black hole might be a little different. It might be a supernova, which will be a huge amount of energy released that would also cause you trouble as a planet. But imagine like in the situation with our solar system, where the star is small enough that it will just turn into a white dwarf and maybe eventually sort of go out and turn into something that's no longer having nuclear reactions happen. What would happen to the planet? As far as the gravity of the star is concerned, doesn't make any difference. If there's a certain amount of mass inside the star, that the gravitational field outside of the star will stay exactly the same. So the planet will keep orbiting. It might get really cold, because there isn't any, there's no energy being produced by the star at that point. But I don't think, the planet wouldn't, the process of forming a neutron star, a black hole, whatever, that's a violent process. And so that would do all kinds of things. But I think once you have, if it was a white dwarf that sort of just went out and turned into a big star made of iron, I think that I don't think there'd be any reason why the planet should do anything other than just keep orbiting its star, albeit, it better have another source of energy. It better be the case that the planet had a bunch of radioactive elements inside it or something that can produce heat, because otherwise you're not getting a lot of energy there. All right, I should wrap up for now. So thanks everyone for joining us here, and be back again next week. So bye for now.